to get started. We are recording. Don't be shy. I know some students now, they're like, oh, I don't want to say anything because I'm going to be on camera. It's just your voice. Most people won't know that it's you. So here's our scenario. We're going to continue what we were working with yesterday, talking about equivalent expressions and ways to write expressions out. Here's our scenario. This swimming pool was designed. It's a big swimming pool. And it was designed so sections can be used for different activities. The dimensions are given. Here, this top section is just for people who want to swim back and forth. This section here is for anyone who's taking a swim lesson. This section up here is for a water therapy, like if there's an injury, water therapy is used because it's really not, it's not as hard on the body and it's low impact. And the last section here is the kids area. Now we don't want to mix the kids and the lax swimmers because if a kid's there, you can hit them, it's dangerous. So we're going to separate. We're going to represent the area of the pool. And I know there it says surface area. It is the surface where the water is. We're going to talk about the area. Why do you think the question, before we even get into the algebra portion, why do you think the question specifies surface area versus just area if you're talking about a swimming pool? This is a little tap into geometry.
Because you can't really see the side, like the other sides of it.
We can't see them, but is there a calculation that would involve them? Yeah, if you just said area, there might be some confusion. Do you mean like the surface on the top, or do you mean the volume of the pool? Some people think of area and they're not sure. So we specify here the surface area. We're just talking about the portion, that you see, that rectangular shape. Okay? So we're going to write different expressions to represent. Anyone have ideas on how you could represent the surface area? We're going to go through 3. But what do we think? Just by looking at it, if you were given this question and you had to come up with one expression to represent the surface area, what would you do?
I think I would do, so first as I'm looking at it, I see that it's even. Everything is correct. So
Okay.
I see that the kids area has 2 x's on the side of it.
Okay.
So it's a square, so those 2 have to be the same x, which means, yeah, it's x.
Okay. So you could figure out the area of the kids area. Okay.
You see that the water therapy is the same size.
Is it? Well, the dimensions are given. Are they the same?
Yes. No.
Anyone want to fight on that? I know they look the same because when I created the rectangle, that this section looks the same. How do you know that the dimensions of the sides are different?
I guess because that one says 8, and then I guess you get X any numbers.
Yeah, in this scenario, we know that this is 8, but we're not sure of this side, so it's X. And I know what you're saying, it looks the same, but for the purpose of the problem, they are different. And the reason we know is because they actually have different side lengths there. But your idea is really good. He started with finding the area of the kids' area. Okay. How else could we have looked at this? Or does anyone want to elaborate on what Mortimer was saying? To find the surface area of the entire pool. Do we see any options? Any other options? What do you think? 25 and 8. What could you do with the 25 and 8? What would you get? And I don't mean the number, but what section would you find if you multiplied a 25 and an 8? The area of what section? The what? Is that the dimensions of the kids' area?
Then we would find the lap swimmer.
Okay, so you could then, if you knew the area of the kids' area, you could then find the area of the lap swimmers. So there's a few ways that you could look at this. Let's start. You could think about the surface area as the area, or the sum, I should say, of the swimming sections and the other sections. Okay, so let's visualize how we could break this up. These 2 sections here involve swimmers, and then these 2 sections here involve other stuff. So look at the image. How did we get this side length here of 8 plus x? We know how this is 25 because this specifically tells us that the length here is 25. How did we get 8 plus x? Manuel.
Well, from the back side, there's 8 and x, and since there's the same line in the middle, you could just move them to the line because it's the same.
So I know that this, let me erase because it's getting a little jumbled now. This side length here is the same as this side length here. We know that, that's the property of a rectangle. We know that the opposite sides would be the same length. But how do we know if the information we're given is that this is 8 and this is x? How do we know that this is 8 plus x?
Because it's
Okay,
squares, it's the same length.
say it again.
They're both squares, it's the same length.
Well, they're not the same length, but if the two sides are the sides of these rectangles. But how do I know that it's not 8x? How do I know that that side length, the whole thing is 8 plus x?
Because there's two lines
Okay.
and you have to add them, but if you multiply them, you're just finding the area of the box.
If we're multiplying, it's not really the correct operation here. The reason we know that this is 8 plus x is because up here, if this is 8 and this is x, then the total would have to be those two numbers added together, the total of them. The difference is, I can't just say 8x. That's not adding 8 plus x. So we would represent it this way. Same concept for this area over here. The 8 plus x follows, and this length is x. Could I find the area of both of them?
What do you mean?
Of these two rectangles. Notice we took this big rectangle here, that big swimming pool, and we broke it up this way. This is one way that you could have visualized this scenario. I'm going to find the area of the swimming area and then the area of the other stuff. What would I have to do with those two areas to find the whole pool? Add them. Once I find them, I can add them. That's one way. That is not the way that you pointed out. The way you pointed out is this way. You could think of the total surface area as all of the sections individually and then put together. So same concept as before. You pointed out, Mortimer, that you knew the area of this was x squared because it was x times x. Again, looking at our concepts of rectangles, if this length here is x, we know this has to be x. So the area here would be what? 8x. So this is x squared. If this is 25, what's this? It's x. So what's the area of my swimming lessons? 25x. And then this top section, my length is 25. My width here is 8. So my area? 200. Once I have all four, what would I do to get my total surface area? Add them up. So my total surface area, x squared, plus 33x, plus 200. You will not be working with those types of equations until the spring, but that's a quadratic equation. You'll see that in the spring. We could, and this is like the last way, there's multiple ways you may see it, but the three that we want to focus on, taking the two big chunks, adding it together, taking each separate section, finding the areas, combining them. You could look at it as 25 plus x times 8 plus x. Who can explain what that calculation represents in terms of the swimming pool? Where did we get 25 plus x and where did we get 8 plus x? Gustavo.
Because if you like add 25 plus x, you're doing one side and like with the other, it's 8 plus x, and you multiply both, you get the surface area.
Perfect. So this scenario actually shows the full pool. This side, if this section is 25 and this section is x, then combined they are 25 plus x. It's not 25x. That's a common mistake. This width here, if this section is 8 and this section was x, combined they're 8 plus x. If I wanted to find the area of the whole thing, I could do that using this type of calculation. That's what we call a polynomial. You'll be doing them more in the spring, but we are going to calculate the one today so you can see how comfortable and ready you are to solve them or calculate them. Okay. How can we show that these are equivalent? Let's go back to yesterday when we were talking about what makes something equivalent. If you want to try in your binders, you can follow along. But what do we have to do to prove equivalency? There's two things we talked about yesterday to prove. Gustavo, what's one of them?
Can you like simplify like all of them?
Yeah, one thing we could do is simplify. Let's simplify each one. This one we actually already sort of simplified on the previous slide, but let's simplify this first one. How do I simplify that? What do you see? And these are good examples for you to write down as we go so that you're familiar with simplifying. What do we see here in terms of simplifying? We have 25 parentheses 8 plus x times 8 plus x. How can I simplify this? Jaden. Okay, I can combine my like terms. What terms are like that I could combine right now? Emmanuel.
8 plus x.
Can I just add 8 plus x?
No, I mean like take out 8 plus x.
Where would you put it?
Like on the other side, it's left, so it's left.
I'm sorry, say that again.
Like, I would take out 8 plus x, move it to the side, and then whatever's left, put it in parentheses.
So you would do that.
Yes.
Is that simple? The simplified, I should say.
Well, it is easier to multiply.
Okay, but is it simplified? Because we do want to make it easier, of course, but we do want to simplify it to get to its most simple state. What are the things we want to keep in mind when we're simplifying? The first thing Jaden said was combine like terms. What else do we want to do when we need to simplify?
Do the multiplication or the distribution.
The distributed property, right? So do we have the ability to do the distributed property right now?
Yes.
We can. What can we distribute? What can we distribute in this one? We're going to start with that one. We're going to do all of them actually. I know no interest in this. What can I distribute here? Goes hand in hand with our warm-up when we were distributing in our warm-up.
What symbol are you looking for when you think of the distributed property? What? Good, parentheses.
Good. The parentheses. Good, Emily. So if I know that the parentheses is there, how do I distribute to remove the parentheses? Think about the question. If I know the parentheses are there, how do I distribute to remove the parentheses? I'm going to multiply. What can I multiply? I can multiply x times 8. What else can I multiply? 25 times 8. Are those the only two things I can multiply? Giselle?
The x and
The x and the x. And Leo, what else?
the 25 to the x.
25 and x. So let's start to do this. 25 times 8
200.
plus
25 x.
plus units plus
8 squared. I mean x squared. X.
now what can I do? No more parentheses, no more distributed property. What next?
You could simplify the x like 25x plus 8x.
I can combine my like terms.
So
Can I add those two terms with x squared?
Wait,
Are we
no.
using
Yeah, but yes. We know. Yes. Maybe.
Can I add 33x plus x squared?
No.
Why not?
Because x squared is to the second power.
X squared and x are not the same variable. They're different. Having something to a power, they're different. So here, can I simplify further? No. I'm done. So that was our first option. Our second option, we actually did it already on the previous slide. We just combined our like terms. This was there. Okay? So we knew that that was the same. And then the last one, I'm going to erase. This is multiplying polynomials. So you will be doing this in the spring. So we're just going to go through and we'll kind of show you Multiplying polynomials, which we will do in the spring, this is like more of the heavy algebra, heavy 9th grade algebra 1. It is really the same thing as the distributive property. Okay, so when you get nervous about algebra 1, you can say, well, I already know how to do that. The difference is you're multiplying, and there's a few different strategies to do this, but we don't teach just one. For now, I'm just going to show. You would multiply the 25 times the 8 and the x, and then you would multiply this term by the 8 and the x. You already did that here. Notice that, and you really, Emmanuel, pointed it out. I'm going to cross this out. You said I would take the 8x and I would move it to the side, and I would take everything that's left and put it in a parentheses. Notice that everything that's left is right there. They're the same thing. So when we get to polynomials and multiplying them, you'll see amazing similarities because multiplying your polynomials is really distributive property. It's just grouped differently. So we proved that they were all equivalent because we simplified everything like Gustavo said. And we ended up with x squared plus 33x plus 200. So now let's say x is 10. What is the total surface area of the pool? If x is 10, what is the total surface area? Try it in your binders. When you have an answer, raise your hand. Emmanuel's got it. Who else? So if x is 10, what do we got? We're just going to see how many other people can come up with their solution. Okay, so a lot of you have it. Now this is a great way to check work. If we were solving an equation and you came up with, I found x is 10, the best way to prove that you're right is to take that 10 and go back and solve it, plug it into the equation that you started with. For those of you that are finishing, we're going to start to walk through it. If I substitute in 10 for x squared, Dina, what do I get if I substitute 10 in for x squared? What's that value going to be? 100. Very good. It's 10 squared, meaning 10 times 10. Common mistake is to say that it would be 20. 10 times 2. 10 times 10 is 100. So we have 100. Next term, 33x. We're going to substitute in 10. So it's 33 times 10. Leo.
330.
Good? Last term. Do we have to do anything to it? No. What's my total? 630. Good. No matter how, if I went back to the original expressions here, all three of them, I still would have gotten 630. If I just plugged in 10 here and did 35 times 18, I would have gotten 630. All of them I would have gotten 630.
This is off topic, but like this is like the question, are you like gonna teach us like about negative exponents?
Negative exponents, yeah. We're gonna do that. I think it's unit 5 about negative exponents. Yes, we are. We'll be simplifying using there are properties of exponents that we will be going with. You won't be doing calculations with negative exponents this year. You'll be simplifying exponents, like simplifying expressions that have exponents. In higher level algebra, I think it's algebra 2, you'll start to calculate with negative exponents. What? Algebra 1 and then algebra 2, and then beyond. Okay. If you know, there's no right or wrong answer here. If you knew the value of x, which one would you use to solve, like to get your value? Which one? There's no right or wrong answer here, it's just your opinion. Which one is easier for you to work through if you know the value of x? What do we think? If you know that x is, let's say 10, which one would you use? Luz, which one would you use?
The last one,
The last one? Why the last one?
because it seems the most easiest.
Yeah, I would probably, I think I would do the last one, that's just my personal, because it ends up just being two numbers that I multiply. Anybody, would you do something else?
I'll probably use one or two.
You like the first or second one? Okay, maybe because of the pool, does it like break it out a little bit easier for you? There's no wrong answer there, but it's just another way to kind of get your wheels turning and to speak to the idea that there's not just one way to solve things or figure things out. Okay, we're not going to do this because this is all review that we know. So we're going to go to this. We're going to write this expression two ways. Okay. So we have 1/2.
So this is on your DOL paper.
You have your paper. Oh no, the one is left alone. Oh no, I can't do that.
It's Wednesday.
So we have an expression here. We have 1/2, and then inside the parentheses, a plus b. Okay? How could I simplify that?
I'm gonna have A plus I'm gonna have B.
It's your deal.
Oh,
But yeah, I like it. Some of you may be racking your brain over the two ways. The one way can be written, the same thing can be written two ways. So as long as you understand the idea behind the two ways, we're